Hi everyone. Today's lecture's topic is interaction effect using dummy variables. Up until now, I have taught you interaction effect between a dummy variable and an explanatory variable. And today we'll study how interaction effect between the two dummy variables results into, very interesting conclusions. So firstly, let's consider an additive model yi equals to beta 1 plus beta 2 d2i plus beta 3 d3i plus beta xi plus ui, where d2 and d3 are your two dummy variables and x is your explanatory variable. So I have dependent variable yi as wages in rupees and xi is level of education in years, and d2 equals to 1 if males, 0 otherwise, which is females here, and d3 equals to 1 if white, 0 if otherwise, that's non-white here. So clearly my d2 dummy is indicative of some gender discrimination with respect to the wages given to males and females. There is some gender discrimination, and my d3 dummy refers to some sort of racial discrimination. So on the basis of race also the wages are being given. It's a very interesting model and it actually shows you the relevance of dummy variables in labor supply. So as a researcher, if you wish to model labor supply decision of let's say a female or male or of anybody in a country, you need to take these particular factors into consideration like race, gender, ethnicity, language, etc. Alright, so moving on to the results. See, step 1 is that you then find out your regression equations with respect to the dummy categories. Alright, now since my dummies are 2 and each of the dummies has 2 categories 1 and 0, I'm going to have 4 different regression equations depending upon my dummy taking certain values. For example, d2 and d3 could take a value of 0, 0, 1, 0, 0, 1 and 1, 1. Likewise, you'll have these regressions and the names. I'll teach you about one of the case and then you can build upon others. For example, if d2 and d3 are both 0, I'm talking about females, those are non-white. Fine. 0, 0, females, those are non-white. So it's non-white females, and putting d2, d3, 0, I'll have beta 1 plus beta xi. Alright, so that's my regression equation. yi hat equals to beta 1 plus beta xi when d2 and d3 are both 0. Next, let's talk about d2 equals to 1 and d3 equals to 0. d2 1 being I'm talking about males and d3 0 means I'm talking about non-white males. So next category pertains to non-white males. So the classic way to construct this particular matrix is to begin in a fashion 0 0 1 0 0 1 1 1. So you can have the 0 0 extreme upward and then 1 1 extreme here. Then in the middle there's a 1 0 and there's a 0 1 here. So that can actually give you a very good matrix, and it's actually serving the purpose of interpretation now. Now let's talk about interpretation. So basically, why have I introduced 2 different dummies? There must have been some objective, right? That I introduced 2 different dummies. So the objective was to bring out both the gender and the racial discrimination. Observations. Differential effect of being a male is beta 2 whatever the race is. See, you have to make the interpretations in the fashion as I have marked here. So step 1 is comparing top 2 categories. Step 2 is comparing bottom 2 categories. Step 3 is comparing first and third. Step 4 is comparing second and fourth. Basically, firstly you have to compare females and males for non-whites. Then compare females and males for whites, which is 1 and 2. Then compare females and females such that, so it's like non-whites and whites in females. Then compare non-whites and whites in males. So keep one of the dummies constant, compare the other. Keep other constant, compare the other dummy. So that's how you have to proceed. Also in interpretation, make sure you're making the interpretation with respect to the category which receives the value 1. For example, right now in my model, D2 equals to 1 for males and D3 is 1 for whites. So my interpretation is going to revolve around males and whites. So I should be able to tell that what is the differential effect of being a male and what is the differential effect of being a white. Differential effect of being a male when you are either white or non-white. So that is one of my interests. And then differential effect of being a white when you are either male or female. I'll repeat. Differential effect of being a male when you are either white or non-white. Differential effect of being a white when you're either male or female. So I'll keep one constant dummy and then look at the others. Likewise here as well. So starting with my 1 and 2. So I'm trying to compare males and females keeping the race constant. So if race is constant at non-white, differential effect of being a male from female is beta 2 because its intercept is larger than beta 1 by beta 1 plus beta 2. So beta 2 is clearly the differential effect of being a male here. Likewise in case of white, differential effect of being a male is, here it is beta 1, beta 3, beta 1, beta 2, beta 3, again beta 2. So what do you see? That differential effect of being a male in non-white and white people is just the same. So that means differential effect of being a male is beta 2 irrespective of the race being white or non-white. So that is my first conclusion from comparing males and females keeping the race constant. Now second step, I'll compare the race keeping the gender constant. Okay. So coming at my third comparison sequence. So differential effect of being a white. So you have to tell the differential effect of category receiving the value 1. Okay? So differential effect of being a white is, compare this regression from this regression because females are constant. It is, I see beta 3. So differential effect of being a white is beta 3 for females. Now let's compare this and this. Differential effect of being a white for males is beta 3 again. So that means the differential effect of having white color is the same irrespective of gender being females or males. So I have my observations here. Differential effect of being a male is beta 2 whatever the race is, and this is coming from 1 and 2 comparisons. And then I have differential effect of being a white is beta 3 whatever the gender is. It means when we compare males with females, there doesn't seem to be any racial discrimination. Similarly, when it comes to comparing whites with non-whites, gender discrimination seems to be absent. Hence, my additive model does not reflect the picture of the society. So, what it is trying to convey is, since the differential effect of being a male, was just the same irrespective of race, and likewise the differential effect of being a white was the same irrespective of gender, I'm not able to convey this gender and racial discrimination through my model. So what do? I need to have one differential intercept which conveys that there is gender discrimination, there is racial discrimination. For that, you need to add an interactive dummy. Now that interactive dummy will be a product of D2 and D3. So now it takes us to the multiplicative model, which looks like this. It is just the same until this point, and also beta xi is there. Only one extra term gets added, beta 4 d2i d3i. Okay, so this is beta 1 plus beta 2 d2i plus beta 3 d3i plus beta 4 d2i d3i plus beta xi plus ui. Again, I have taken those 4 categories. I'm not going to repeat it. You can have a moment at understanding how these values were derived. These are the same. D2 is 1 for male and 0 for female, and D3 is 1 for white, 0 for non-white. Substitute values 0, 0, 1, 0 and so forth in this model, and you will have this regression equation. This should be y I hat. So I'll have non-white females, non-white males, then white females and white males. Again, interpretation is always made with respect to the category receiving the value 1. So I am interested in finding out differential effect of whom? Of male, and differential effect of white people. So when I'm looking at males, I'll actually keep race constant. And when I'm looking at white, I'll keep the gender constant. So again, my matrix is helpful. 0, 0 on the top, 1, 1 in the end, then 1, 0, 0, 1, like an identity matrix. So this is first comparison. Second comparison will give me my first observation. Third comparison and fourth comparison will give me my second observation. So first observation. Let's try to understand the differential effect of being a male. Keeping the race constant at non-white, differential effect of being a male is beta 2. Here it is beta 1, here it is beta 1 plus beta 2. So fairly simple. Differential effect of being a male in non-whites is beta 2. Then differential effect of being a male in whites is, there we have beta 1, beta 3. Here we have beta 1, beta 2, beta 3 and beta 4. So this is beta 2 plus beta 4. Okay. So differential effect of being a male in whites is larger than the differential effect of being a male in non-whites. So I think it's a good result. So we have actually seen that, gender discrimination is vital, in white people. So there is prevalence of gender discrimination. Now let's look at the racial discrimination. So I'll compare females with females such that one is non-white and one is white. Then non-white males with white males. That is third and fourth observation. So differential effect of being a white. You always talk about the differential effect of the category receiving one, which is white. So differential effect of being a white for females, comparing these two, is beta 3. Then differential effect of being white for males, comparing this one and this one, is beta 3 plus beta 4. Okay, so yet again we do have a good number. So we see that differential effect of being a white for males is actually higher. So we have our two observations and we have clearly proved that in this particular model with an interactive dummy, we have actually shown gender and racial discrimination. So the results are summarized over here in the observations. Differential effect of being a male is beta 2 for non-white and beta 2 plus beta 4 for whites. Then differential effect of being a white is beta 3 for females and beta 3 plus beta 4 for males. It means that in comparing males with females, for racial discrimination plays its role, and similarly when we compare whites with non-whites, gender difference also participates or plays a role. So that ways we have been able to develop a good model to give us a picture of the gender and racial discrimination in the society with respect to the wages given. Now let's do a very quick question on the same. This is a question where you have two models, 1 and 2. Dependent variable is hourly wage in dollars. Independent variable is education, years of schooling. Then you have two dummy variables. D2 is 1 if female, 0 otherwise. D3 is 1 if non-white, 0 otherwise. Here otherwise refers to males. And here also it refers to whites. So let's proceed with the question. So this is your regression model. These are the T observed values as reported in the regression. So these are the T observed. Again, these are the T observed. So this model is continuing from here to here. This is minus 0.2, minus 0.2, minus 1.7 D3I plus 2.12 D2I D3I plus 0.8 XI. I haven't spoken all the decimal figures. I think you can do the job. So that way this is your regression model. It looks fine. Just that in model 2 I have an interactive dummy. In model 1 I do not. So model 1 is an additive model and model 2 is a multiplicative model. So part 1 of the question says, are the differential intercept coefficients for both the models statistically significant? So I need to check all the coefficients of dummy variables which actually act like differential intercept coefficients are significant or not. That means I need to check beta 2, beta 3, and here again beta 2, beta 3 and beta 4 for their statistical significance, because ultimately these act like the differential intercept coefficients now. Like you can see here, these beta 1, beta 2, beta 3, beta 4 are the ones who act like differential intercept coefficients. So I need to check their significance. Also this model is very interesting. The output is the same till beta 3 D3I, only for beta 4 it is different. So testing either ways is the same, since it is minus 2.36 here and same values are here. So null hypothesis will be beta 2 is insignificant. That means beta 2 is 0. Then alternative is beta 2 is significant. So that could be beta 2 not equal to 0. Now you may be arguing that why we haven't taken beta 2 less than 0. You can take, again it's your choice here, since underlying theory right now says that beta 2 should be negative, as has come in the model. So you can take that as well, and not equal to 0 as well, doesn't matter. Alright, so also I forgot to tell you one thing. The single star on the t value is indicative of p values greater than 5%. I'll repeat. The single star on some t values, as you can see in the output, is telling that p value or the probability value for that particular intercept is greater than 5%, and of double starred means that it is less than 5%. In a way, the double starred coefficients are significant, because if p value is less than alpha, we reject the null hypothesis of insignificance. So I have my null, I have my alternative. Now it really doesn't matter if your alternative is not equal to 0 or less than 0. All you have to do is look at the p values. So p value here, since it's a single star, is greater than it's a single star here. Single star means less than 5%. I'll write it for you here so that you don't have a confusion. I might have spoken wrong, I doubt. So p value, single star is less than 5% and double star is greater than 5%. Fine. So less than 5%, reject the null, beta 2 is significant. Again, it is single star, the p value is less than 5%, reject the null, beta 3 is also significant. However, your beta 4 has 2 stars, that means p value is greater than 5%. So you're not able to reject the null hypothesis and it is insignificant. So the test is being done here. Since p value is less than 5%, H not rejected, beta 2 is significant, beta 3 is significant, but beta 4 is insignificant. So you have done the test. Now let's talk about part B. Part B says interpret the differential intercept coefficients of both the models. So you have been asked to finally interpret the differential intercept coefficients, which we have been doing up until now. So what is your step? Step 1 is to make all 4 categories depending upon the 2 dummies which you have. D2 is 1 for female, 0 if male. D3 is 1 for non-white and 0 if non-white. These are my combinations 0, 0, 0, 1, 1, 0, 1, 1. So you can go about it in the same fashion as I taught you earlier. Then these will be your regression results. This is for model 1 and this is for model 2. I'll just begin with the interpretations. So we always talk about differential effect of being the category which receives the value 1. So in my model, the D2 is receiving a category 1 if female and D3 is 1 for non-white. So I'm going to talk about the differential effect of being a female and the differential effect of being a non-white. So in model 1, again comparing in the same fashion, nothing has changed. Step 1 was making this particular matrix. Step 2 is marking this as 1, 2, then 3, 4. Then 1, 2 will give you observations for females and 3, 4 is going to give you observations for non-white. So I have it again here. Differential effect of being a female, because my female receives a category 1 for non-white people. Okay. So keeping non-white constant, differential effect of being a female is coming out to be beta 2 as I have written here. So differential effect of being a female is beta 2 in non-whites, and let's check for whites. So it's beta 2 again. So differential effect of being a female is beta 2 for whites as well. So we see that the differential effect of being a female is beta 2 irrespective of the race, white or non-white, since it's an additive model and we knew that this is the result which we are going to get. This is about model 1. Next is differential effect of being a non-white. So we'll compare females with females such that one is non-white and one is white. So differential effect of being a non-white can be seen beta 1, beta 2, beta 3, beta 4, beta 1, beta 2. So beta 3. So it's beta 3 in females, and for males I have comparing this fourth part, non-white males with white males. I'll have differential effect of being non-white for males is beta 3 again. It's here. Alright. So we see that differential effect of being of female is beta 2 irrespective of the race, and differential effect of being a non-white is beta 3 irrespective of gender. So clearly gender discrimination, as I've written GD, and racial discrimination RD doesn't really show up when they are interacting. So it's just the same irrespective of gender, it's just the same irrespective of race. Next, I'll interpret my multiplicative model, and again those 4 comparisons, 1, 2, 3 and 4. So differential effect of being a female, let's talk about non-whites. So these are my non-whites, this is female, male. Differential effect of being a female is, I have beta 1, beta 3 here, beta 1, beta 2, beta 3, beta 4 here. So I have beta 2 and beta 4 extra. So that means differential effect of being a female is beta 2 plus beta 4 in non-white. And let's now look for whites. So differential effect of being a female for whites is beta 2. So clearly there's a difference. For non-whites it is beta 2 plus beta 4, whereas for whites it is beta 2. Then differential effect of being a non-white. Now to do that I look at this third combination. Differential effect of being a non-white for females is beta 1, beta 2 here, beta 1, beta 2, beta 3, beta 4 here. So it is beta 3 plus beta 4 for females. And for males, non-white males with white males, I have beta 3. So differential effect of being a non-white is beta 3 plus beta 4 in females and beta 3 in males. So clearly I have a good result. So interactive dummy has done a good job in bringing up the gender and racial discrimination. So that was about part 2. Let's see what part 3 says. Part 3 says, are the results of model 2 indicative of gender and racial discrimination significantly? So they are saying, please check if the results of model 2 are indicative of racial and gender discrimination significantly. So I need to check whether beta 2 plus beta 4 is actually statistically different from beta 2 or not, and whether beta 3 plus beta 4 is actually statistically different from beta 3 or not. In a way, what do you need to check? So these two are equal and these two are equal. For that, I need to prove beta 4 is 0. So beta 4 is 0, then beta 2 is beta 2. Same in both the models. And here also beta 3 will be beta 3. So my null hypothesis is to check for beta 4 being significant or not. So null hypothesis is beta 4 equals to 0. No gender or racial discrimination. Alternative is beta 4 is significant, that is there is gender discrimination and racial discrimination. Now let's look at the p-value. This is my beta 1, this is my beta 2, this is my beta 3, this is my beta 4. I have 2 stars. 2 stars means p-value greater than 5%. So unfortunately, I am not able to reject the null hypothesis of insignificance. So since null is rejected, beta 4 is insignificant. There is no gender and racial discrimination. That is, results of model 2 are not indicative of gender and racial discrimination. So that ways, I think it was a very good exercise to understand about the multiplicative model, how it has been an improvement over the additive model, and why interaction effect using dummy variables is too important, especially in, for example, labor markets, so basically labor supply and labor economics. So thank you for watching the video. We will follow with the next topic again.